is all the trajectories for large scale action recognition is obviously by
Good afternoon, everybody. Thank you all very much for coming to my presentation. I will be presenting my topic on order trajectories for large-scale human action recognition. Myself is Oruganti, from University of Canada. So, the outline of my presentation is, first of all, I will give introduction, very basic about all area of human action recognition, and the motivation for order trajectories and the total framework, and some other settings we have taken to conduct our experiments, and finally we will show the results of our technique on two data sets, and we will also present the child's data set UC101. So the basic framework for an action recognition is having video, computer detection, you determine some regions of interest, that is the interest point, and then you compute some local descriptors around them. Essentially, they are going to capture some shape, motion, such kind of things, and then you construct this from them, and then you develop the test. So, some of the interest points which are quite popular in this field is like local interest points, like so they show the space-time points which are very in time scale. But one of the bad drawbacks is that they miss global information and only trigger when significant spatial temporal changes. Another kind of technique is the body part detectors. That means you have detectors for head, legs, torso, and limb. So on each frame or some key frames, you detect those body parts. And using that information also you can detect the action recognition. But this is useful only on small scale, but on large scale, this is difficult because they do not at all capture any context. So, an popular technique, and which has been presented before me, and many people have used in the channel also, to consider like this, in which a sequence of interest points are tracked for a extent of 15 frames per second, 15 successive frames. So, now, the local descriptors are computed around such kind of interest points, which are detected by different techniques. And I want to here describe, emphasize on the point that when there is some interest points detected, you around some subvolume defined by n segment and tau in space and time, and that is these descriptors like or motion ball histogram are computed. Now, the motivation for our technique is, if objects that move for longer time are captured, then they are able to contain more cache information. Like from the previous presentation where our friend Silvio, he was saying in developing a hierarchical model, suppose we have trajectories A, B, C, D. If you can combine A and B or C and D, that in the right way, will it improve? So I think that's also one of the, it comes close to our motivation. But the problem is, how can you compute a descriptor around varying length of interest points? Suppose there is a track which has 100 frames, which is track of 100 frames. Then the half descriptor or ambiguous descriptor is n sigma and tau, and tau will change basically. Whereas if you have a small track which has only 5 frames, its descriptor will be different. Then how can you combine those different length of descriptors? So the solution we propose is the order trajectories. So order trajectories means basically the trajectories with longer duration, and we just accumulate the local descriptors of the order trajectories. We will not compute descriptor over one full length trajectory, but only the basic constituent trajectories which constitute a long trajectory. For example, if we show in this figure, there is one track trajectory starting from frame I. There is a second trajectory starting from the next frame I+1. So, if this trajectory is essentially this trajectory only, but continuing from the next frame, we are essentially having two tracks. But if we combine both of them, that's a longer trajectory, and trying to use that descriptive sequence very special way, we are hoping that will give better recognition rate. So, a technique to match two kind of trajectories between two successive frames is brute force technique is ransack technique. But we propose here a computationally simpler technique. That means, suppose we have this trajectory, want to compare with this trajectory in the next frame. We will not compare all the points. We just compare the second point of the first trajectory and first point of the second trajectory. If this distance is less than a threshold, which has been chosen based on the tensor trajectory, which is computation, then we'll label it as this is a trajectory that is going to continue from the next frame. It's a very simple technique. So, essentially, matching of two dimensional trajectories has been reduced to just certain matching of 2D set of points. So, this doesn't take much time. And so the exponential which we have used to test our framework is we are taking a simplest backward model. We first compute test trajectories, and then we generate the order trajectories, which are longer ones, and then we compute local descriptors around them. We construct code books and construct testing models. We use this following four descriptors of based trajectory shift. So we have experimented with different kinds of encoding schemes. Just a brief introduction for others have already covered it. The first technique, which is very popular, is the hard assignment scheme, in which basically captures the frequency of the visual words. So we constructed code books of 4,000 visual words using k-means clustering. So in this technique, the feature dimension is 4,000 for each descriptor type. And then we use multi-channel nonlinear SEM with RPF chi-square, kernel chi-square, each class. The second type of feature encoding technique we used is VLAB technique. So the difference is that it just doesn't count the frequency. It tries to capture how much the descriptors are closer to visual words. So the degree of difference, so basically it's trying to capture something like first order information. So for this purpose, the code books of 256 only visual words are constructed using k-means clustering. And because we are using the difference, not just frequency count, so the dimension of the descriptor becomes fixed. So the length of the feature dimension, length of the feature is 256 into d, where d is the dimension of the descriptor. If it is a half, 96. If it is static shape, it is 30, and it varies like that. And in this case, because they are not histograms, we cannot use chi-square kernel or nonlinear square. But what we can do is we can concatenate all the features, and because now the feature is very long, we can directly use a linear SVM. And the third kind of feature encoding technique is Fisher vector. And the Fisher vector encoding technique, it tries to capture the first order and the second order statistics. So it captures the deviations and the deviations of the covariance also. In that sense, essentially we can think that this is going to capture much more information than hard assignment or VLAB technique. So the code books for this technique are constructed by using corresponding model, and the feature dimension size is 256 into 2D, because 256 into D is for the deviations in first order, and for the second order 256 into D. Together they are doing 256 into 2D. And in this case also we concatenate all the features and directly use linear SVM. So these techniques of VLAB and Fisher vector encoding are quite popular in large-scale image classification, and recently only they have been started applying on dimension recognition, particularly on large number of classes. So that is where we try to do this technique. And we use one against test multi-class classification performance measure, and we tested our technique on two datasets, HMDB51 and USF50. They are collected from real-time scenario scenes, and each one has at least 50 classes. That were largest datasets till date. So now I'll come to the results part. So I'll give you an idea on how many number of audit trajectories are there in suppose videos. For example, video from HMDB51 dataset, the dense trajectories, which is space trajectories, is around say 21,000. The audit trajectories is nearly only 50%, 7,657. So they are quite few in number, and actually this can enhance computation efficiency that I am showing in that computation. And this is the distribution of the ratio of number of audit trajectories to the number of test trajectories for all the HMDB videos. So for most of the videos, say 1600 videos, it is around only 50%. For some videos, it is around 90%, and for some it is 0.1%. But seeing the Gaussian distribution and the average around 50%, you can safely assume that nearly 50% of dense trajectories are sufficient for what we are using in our experiments. Now I'll come to the recognition accuracy on the datasets. So the dense trajectories have yielded 84.5 and 46.6 on the two datasets. And the proposed audit trajectories, which are nearly only half in number of the original dense trajectories, have yielded 85.5% and 47.3%. So this is on par and better than the percent dense trajectories. Now dense trajectories, when computing special pyramid, that means there is a lot of computation efficiency. It is 85.6 and 48.3, which is very close to our audit trajectories. There is a recent technique in CVPR 2013 where they have shown that randomly sampling 10,000 descriptors, dense trajectories, on an average of 5 times, they have yielded 83.3% and 46.6%. So it is because of randomly selection. If they run for 10 or 15 more times, this will come down or this will go up. But the idea we are taking is that the dense trajectories are so rich, but a few of them is selected properly. That means in an ordered way, we can get a much better recognition data. So one of the byproduct of our results is that the background noise like things is lessened because we are taking the trajectories which are of longer duration. Some of these things have degrees. For example, in one of these videos from UC50, we can see that some of this background has disappeared. In another video from HMD51 dataset, some background like this noise is lessened. So, because
the reason that the background trajectory disappeared because of what? Because I thought you're taking a couple of trajectories and getting bigger, longer.
Yeah, we are checking are they continuing or not for next coming frames.
So that will remove also smaller.
Yeah, as a consequence, some of them may be removed because we are not specifically focused. It's just naturally coming up. So it is giving a support to our technique that longer trajectories, the other trajectories which we are collecting, is richer enough.
So before merging, there were maybe two trajectories that would correspond to the order trajectory, or 2 or 3 or maybe n. But afterwards, it's just one. So you're actually downweighting the presence of these long trajectories in some sense, basically, right?
No. What we are doing is, suppose it's trajectory A, trajectory B, and we have found out that it's the same trajectory that is going to continue.
Yeah.
We just accumulate descriptors of this trajectory and this trajectory. That's all.
I see.
We have not so far matched it. We have kept it for whichever. So in that way, we just have to collect the indices of the trajectories, which are just computing. So it doesn't even take space also.
So, but then what's the advantage of doing that? If you are keeping the descriptor for both the trajectories, right?
Yeah.
Why do you do that?
Yeah. The point is, first thing is there is computation efficiency, because I am showing that by results that the results which have been obtained by Gaussian trajectories, spatial pyramidal style, different kinds of encodings, contractation, all of them can be achieved by just almost half of the actual trajectories. Because the feature dimension, the length of the feature dimensions which are shown like 4000 into d, 256 into 2d, and they're used in a spatial pyramid style, they are going to increase like anything. And you have to construct code for each time, and we will transfer.
So you just have more context representation person.
Yeah,
That you are not losing because we have fewer trajectories.
Yes. It's, right now, we are the main point we are showing is that even with less trajectories also, we can get on par or better performance. Especially on large scale, when in the future the number of plots are going to increase, this will be used. So I'm showing the video now. So we can see there's some background as well. And now the results on the challenge dataset, user 101. So the proposed order trajectories using hard assignment was 72.8, which we published in the research track, and using Wheeler technique is 73.1, and then proposed order trajectories with Fisher encoding technique is 80.1. Obviously, it is more than a 7 to 8% difference because it's capturing first order and second order statistics. And the improved trajectories, which was proposed by Wang and Smith in SCV 2013, is 83.6. So, although we did not compute the order trajectories immediately, improved trajectories because of time, on which they raised the code, we have just used the improved trajectories and our order trajectories information. There is an improvement of around 2%, which shows that it is complementary. And as shown in the result, the improved trajectories when computing spatial pyramid style gives 85.9, whereas the other trajectories gives 85.4. That is just 0.5 difference, but there's a lot of decrease in computations. So the conclusion we can say is dense trajectories with longer duration can definitely yield on par or better performance than dense trajectories, and this can be a very good tool for computation resources. And the proposed order trajectories are also complementary to the recent improved trajectories and have yielded very better good recognition rates on the channel dataset. And as a byproduct, noise-like trajectories are also lessened by. Thank you.